This is a roughly 1/72nd scale model of Poe Dameron's X-Wing starfighter from Star Wars: The Rise of Skywalker.
Behind us is a full-scale screen-used X-Wing. It's hanging here in the National Air and Space Museum in Washington, D.C.
You should really come see it. It's cool. But what does a 1/72nd scale model actually mean?
That means it would take 72 of these models lined up wing to wing to cover the wingspan of our X-Wing fighter.
Today, we're going to be looking at some really mind-bendingly big things.
But we're going to show you how to think about them in smaller, more user-friendly models.
This is STEM in 30.
We're going to talk about scale. Not the thing you weigh yourself on, but the math concept.
Scale is the ratio between the size of a given original object and a new object, which is a representation, but of a different size. These can be bigger or smaller.
For what we're talking about today, we're going to show you smaller models to talk about larger objects.
An easy way to think about it is this. If you come to the museum and you want to find your way around, it'd be pretty hard to walk around with a map the same size as the museum.
So we scaled down the size of the museum to fit on a piece of paper, which you can fold and put in your pocket.
Maps aren't the only thing done to scale. Scale models are everywhere.
We sell models like this in our gift shop.
One of my hobbies is building little things, but all the figures and pieces need to be the same scale or they look funny.
I built this model of a Missouri River flatboat when I was in 4th grade, and yes, I still have it.
Most commercial models are to scale. Just look at the box and it'll say what the scale is.
Model trains are a great example of scale models, and different trains have different gauges based on the distance between the rails they run on.
These are S-scale trains, which means they are 1/64th scale.
Even the museum uses scale models. We have a 1/100th scale model of the USS Enterprise aircraft carrier. Even at that scale, it's almost 12 feet long and includes 83 aircraft, tugs, fuel trucks, fire trucks, forklifts, and a crane.
We also have a 1/10th scale of the Lockheed Electra, the type of plane Amelia Earhart was flying when she disappeared.
And behind us, we have a scale model of the planets in our solar system.
The Jupiter model is 15 feet across, and all of the planets and moons are properly scaled to each other. Based on Jupiter having a diameter of 86,881 miles, you can calculate the scale. This means this scale model is approximately a 1 to 30.6 million scale.
Planets are really big.
And we use scale models here in the museum because we can't fit things like aircraft carriers and planets in here.
Find a museum near you. Look around and see if they have any scale models. Let us know about them down in the comments section.
Scale models are a great way to think about really big things.
And we are talking about really mind-bogglingly big numbers.
It's okay if you can't completely wrap your head around just how big these numbers are.
For example, if you've lived for 1,000,000 seconds, you're 11 days old.
If you have lived for 1,000,000,000 seconds, you are 31 years old.
And if you lived for 1,000,000,000,000 seconds, you're dead.
Or you have lived to be 31,709 years old.
To describe the size of the universe, Bill Nye, the science guy, once said, "We are just a speck, on a speck, orbiting a speck, in the corner of a speck, in the middle of nowhere."
Thinking about the universe being full of specks is one way to wrap our mind around these numbers. In fact, the pale blue dot is a photograph of the Earth taken in 1990 by NASA's Voyager 1 at a distance of 3.7 billion miles from the Sun.
And the Earth does seem like a tiny speck of light in this photo.
On the other hand, Carl Sagan said, "Oh, I said there are maybe 100 billion galaxies and 10 billion trillion stars. It's hard to talk about the cosmos without using big numbers."
So it's hard for people who make a living describing the universe
to describe how big or how small the universe is in simple, understandable terms. We're going to help you think about these really big numbers through scale models.
We're going to show you ways to wrap your head around really big things.
And some of them are so big that we can't measure them exactly.
In those cases, we'll use approximations or our best guess as to their sizes.
Large numbers like 100 billion are awkward to write out. 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. So many zeros.
To avoid writing all those zeros, scientists use a shorthand called the powers of 10.
Here we have 1 penny. It is 1.52 millimeters thick. If we stack 10 of them up, we get 15.2 millimeters.
Let's ramp it up a bit. 100 pennies is 152 millimeters. This isn't a huge stack, but it's not easy to do. As a matter of fact, the world record for stacking coins into a tower in 1 minute is 89. This is a stack of 100. Now things get more difficult.
1,000 pennies, or $10 worth of pennies, stacked up gets to 1.52 meters. That's taller than most middle schoolers.
A stack of 10,000 pennies is almost 50 feet tall. A 5-story building is about this height.
A stack of 100,000 pennies? Now we're talking some money. $1,000. That would give us a stack almost as tall as the Green Bank Telescope in West Virginia. And trust us, it's tall.
$10,000 in pennies, or 1,000,000 pennies, gets us to almost a mile. Denver is called the Mile High City because it's a mile above sea level.
Our stack of 10 million pennies, or $100,000 worth of pennies, will need a flashing light on the top to alert airliners. This is up where they fly.
Now we are millionaires in pennies. 100 million pennies. When you stack that last penny, you better have your spacesuit on. You are well above the Kármán line, the altitude that once you pass it, you're considered an astronaut. Fewer than 1,000 humans have ever been up here.
$10 million all in pennies, or 1 billion pennies, is a bit hard to visualize because there isn't much up this high, just a few satellites. But here's what the Earth looks like from this altitude. The power of 10 gets us to really big numbers really quickly.
We have a way that you can scale things up using the powers of 10.
This is something that you can try at home.
Hi, I'm Ella.
And I'm Bryce. We're going to show you how the apparent size of an object changes as we move away from it. We'll be viewing it from 3 different distances: 1 meter, 10 meters, and 100 meters. Each move back increases by the power of 10. Here are the things you will need:
3 copies of Power Viewer Grid, 3 plastic baggies, a ruler or a straight edge, cardboard, an X-Acto knife, tape, a permanent marker, and something to measure with. The first thing you'll want to do is tape your viewer grid onto a table. Place one of your baggies over the viewer grid. Tape it down if you need to. Carefully trace the grid using a ruler or a straight edge. Repeat this 3 times. Next, measure the width and length of your see-through grid. Draw this in the middle of your cardboard. Then cut a hole in your cardboard the size of your grid. Repeat this process 3 times. You should now have 3 power viewers.
Now choose a model that won't move, something like a tree or a house. Your pet isn't a good model because they won't stay still enough. We're going to use a house as our model. I'm going to start at the front door and measure 1 meter away from the doorknob and mark it on the ground with a piece of tape. Next, I hold up my grid and outline what I see on my power viewer.
Once that drawing is done, set it to the side and take out your next power viewer. Measure a distance of 10 meters from the house. Draw what you see in the power viewer. Finally, measure a distance of 100 meters. This is almost the length of a football field. Use your third power viewer to draw your model the same way from this distance.
Take your 3 drawings and line them up. Drawing 1 is 10 to the 0, or 1 meter. Drawing 2 is 10 to the first, or 10 meters. And drawing 3 is 10 to the second, or 100 meters. What do you notice about the drawings? What can that tell you about the powers of 10? Do you think you could see your drawing from 1,000 meters?
Share your drawings in the comments section.
The powers of 10 can help us visualize how big and how small things are by comparing them to each other.
But what if you wanted to calculate exactly how big something is? Something really big, like the circumference of the Earth. How do we measure the circumference of the Earth? Today, we can measure it by using modern tools like satellites and computers. But over 2,000 years ago, a man named Eratosthenes calculated it by using the sun, some sticks, and math.
Our friends Blake in Hawaii and Angela in Kansas City are going to help us measure the circumference of the Earth using the tools Eratosthenes used.
Hi, I'm Angela Bentley, and I live in Liberty, Missouri, which is just on the outside edge of Kansas City.
Hey, I'm Blake, and I live in Hawaii. And today is one of 2 days of the year when the sun's going to pass directly overhead. It happens at 12:29 today, so if I can manage to plant this stick so it's pointing straight up and down by 12:29, then when the sun's overhead, it should cast no shadow.
We know that the Earth is a sphere, which means there are 360 degrees around from the center of the Earth. We're going to take advantage of Lahaina noon, where our stick in Hawaii is casting no shadow.
The sun's rays run in parallel lines, so if a stick in Hawaii isn't casting a shadow at the same time on the same day that a stick in Liberty casts a shadow, it proves that the Earth's surface is curved. But you probably already knew that.
While there's no shadow where Blake lives at 12:29 Hawaii time, here in Liberty you can see that our shadow is measuring at about a 55.5 degree angle.
That means that Hawaii and Missouri are 55.5 degrees apart on the 360 degree surface. We know that there are about 3,833 miles between where Blake is in Hawaii and where Angela is in Missouri. Knowing these things, we can plug those numbers into an equation to calculate the circumference of the Earth.
55.5 degrees over 360 degrees equals 3,833 miles over x miles. X is the circumference of the Earth. To solve this problem, we cross-multiply. Unfortunately, these aren't easy fractions to reduce, but we know you can do it. 3,833 times 360 gives us 1,379,880. 55.5 times x gives us 55.5x. Our new problem is 1,379,880 equals 55.5x.
To solve for x, we need to divide both sides by 55.5. 1,379,880 divided by 55.5 gives us 24,862, which is really close to the actual circumference of the Earth, which is 24,901 miles.
And just think, 2,000 years ago, Eratosthenes was able to estimate the circumference of the Earth very accurately, just using the sun and 2 sticks. Once we know the circumference of the Earth, we can use that information to create a scale model of the sizes and the distances from the Earth to the Moon.
You can try this at home, but we decided to bring in some experts.
We had to pull a few strings.
This is astronaut Kjell Lindgren. He's holding a basketball. This basketball represents our Earth.
This is astronaut Jessica Watkins. She's holding a tennis ball. It represents the moon.
The Earth is quite a bit bigger than the moon. The size difference between a basketball and a tennis ball is a really good scale representation of the sizes of the Earth and the moon.
But how far away is the moon from the Earth? If Jessica takes our moon model and starts to walk away, how far away does she have to go to represent the distance between the Earth and the moon?
Let's do a little math. We know the Earth has a circumference of about 25,000 miles. We also know that the moon is about 240,000 miles away. If we divide 240,000 by 25,000, we get 9.6. If we wrap a string around our Earth model, the basketball, 9.5 times, that should give us a good approximation of the distance from the Earth to the moon.
This is astronaut Bob Hines. He's got some string. Let's wrap the string around our Earth 9.5 times. If Jessica takes one end of the string and Kjell holds the other, we can see an approximate scale model of the distance from the Earth to the moon.
Soon astronauts will once again be walking on the surface of the moon. And with this model, you can see just how far that is.
Size of the Earth? Check.
Distance from the Earth to the moon? Check.
What if we could use the size of the Earth to figure out how big the Sun is?
Here's a really fun way to show the comparison of the size of the Earth to the size of the Sun.
Let's pretend this bowl is about the size of our Sun, and this mustard seed is about the size of our Earth. It would take about 1 million mustard seeds, or Earths, to fill up our bowl.
It would take 1 million Earths to fill up the Sun.
If you didn't understand our mustard seed scale model, there's still time to catch up.
Here's another fun way to compare the Earth to the Sun. Let's say that this is as wide as the Sun. Then that means the Earth is about the size of my thumbnail.
Here's another fun way to look at the sizes of the planets with a solar system in a bag.
Hi, I'm Miss Dabney, and today we're going to make a solar system that will fit in a bag.
These are the things we will need to create our solar system in a bag. A balloon that's about 10 inches in diameter to represent the sun, a variety of seeds, ping pong balls, and a 20 millimeter bead, index cards, something to write with like a pen or a pencil, and rulers. To start, we will use the balloon as our sun. Everything else will be on the same scale. The scale we will be using is 1 to 7 billion. That means for every millimeter we use on our model, in real life, it would be 7 billion millimeters or 7,000 kilometers.
I put you all into groups. With your group, you're going to go ahead and write down all of the planets on individual index cards. There's a bag that has a whole bunch of materials in it. You're going to make some guesses about which material might represent the size of which planet. By the way, you may not use everything that's in the bag, and some materials you might use 2 of. Walking around and having conversations with each and every group, your thinking is amazing. I do have something in my hands that might be helpful. So I do have the actual diameter in kilometers of each planet and the sun. This is gonna help you kind of determine if the material that you chose really makes sense for that particular planet. See if you need to make any adjustments with the planets, maybe with the sun and all of that. Are you ready for the reveal? Yeah! Okay. All right, so the sun is the balloon. Mercury is a chia seed. Venus is a lentil. Earth is also a lentil. Mars is a chia seed. All right, let's talk about Jupiter. Jupiter was not the golf ball. It was actually an M&M. Saturn was not an M&M, it was a marble. Uranus, which is the bead. And then we also have Neptune, which is also the bead. So what do we notice about Uranus and Neptune? On this scale, they're about the same size as well. I feel like something's missing. Do you guys notice something missing? Yeah. What do we notice that's missing? Pluto is missing. Why do you think it might be missing? Why might it be missing? Chris?
Because Pluto is not a planet, it's a rock.
So Pluto is now in that dwarf category, but the reason it's missing is because if we showed Pluto on this scale, it would actually be smaller than this.
I can't even see. Wow.
Not only are the sizes of celestial objects big, but so are the distances between them.
Don't worry, wipe that frown off your face. We've got an activity to help you learn about the distances in our solar system.
By using toilet paper.
Hi, I'm Miss Lampke, and we are going to be looking at the distances between our planets using a scale model. Today we're going to be using toilet paper to create that scale model. On this model, every inch represents 7,710,000 miles. So that means like from here to here, 7,710,000 miles, 7,710,000 miles, so on and so forth, right? So now we're starting to think about how far away these planets are from the sun. Talk amongst your groups really quickly. Where do you think every other planet is in that distance? Go.
Earth, Mars. I feel like it's more. Sometimes it's hard to show up on paper.
Okay, now you guys are starting to think about that scale, right? Because that scale is 7,710,000 miles. So initially you guys are probably like, oh, it's maybe 100,000 miles away. But now that scale is getting bigger and bigger. So when we go out there, you and your group mates are going to get a piece of tape. And I'm gonna give you all a marker as well. What you are going to do is you're gonna think how far away is Pluto with our door being the sun, okay? From then, you all are going to mark the other 8 planets in our solar system, starting with Mercury, okay? So if you put Pluto really, really far away, you gotta think about, well, where are all those other planets going to line up? I want you and your group to kind of figure out where do you think Pluto is going to be. You guys go together. I'm going to give each team a roll of toilet paper. The first square is going to be the sun, and you're gonna start it right here on this black line, okay? As you keep going down, you're gonna figure out, okay, where's Mercury? Then you're gonna stop and you're gonna draw Mercury and label it. I'm going to give you a key to help you out. See if your predictions were a little off or pretty close. There you go. As you draw your planets, markers are the easiest to use, but be careful that you don't rip one. See what I did there? Note that the planet drawings are not to scale. On this scale, the planets would be very, very small, too small for us to draw. Teachers, you can adapt this activity to include math by only giving students the distances to the planets. Then have them calculate the number of squares of toilet paper based on the distance to Mercury being 1 square. Earth is 2.5. Mars is 3. Then you get all the way up to Jupiter and it's 12 squares out. Quietly and carefully come back into the room, back to your spot, and then we're gonna discuss some things. How was your prediction different or similar to what you actually got? Alice, what did your group find?
So it was very far off.
Very far off. Is there anything that you know that is in our solar system that was missing from your model? Cheyenne? The moons, right? We know that not just Earth has moons, but a whole bunch of other planets have moons, right? One last thing I want to leave you guys with. How would our model change if we maybe did this with another galaxy? Would we need a lot more toilet paper or the same amount? Wes?
We're gonna need a lot more toilet paper.
That's a lot of toilet paper.
Let's head out beyond our solar system.
Voyager 1, which took these images, was launched in 1977. It is the farthest human-made object away from Earth. Right now, it is almost 15 billion miles away. That's a long way, but we're going to explore much larger distances.
To give you an idea of the scale of these things, here's an image of NGC 2336. It is the quintessential galaxy photo taken by the Hubble Space Telescope. We've added a banana for scale. Just kidding. This galaxy is huge. It is 200,000 light years across and is located approximately 100 million light years away from Earth. At this distance, it's hard to see individual stars, much less a banana.
Beyond our solar system, if we want to measure things, we don't measure in miles, but in light years. That's the distance that light travels in 1 year, or 186,000 miles per second. That translates to 5.88 trillion miles per year. When we talk about 1 light year, we are talking about almost 6 trillion miles. And around these parts, we're talking about a lot of light years.
The closest star to us, besides our Sun, is Proxima Centauri, which is 4.2 light years away. Remember, that's over 24 trillion miles.
When you look into the night sky, you see stars of different brightnesses. That doesn't mean one is closer than the other. Some stars are huge, others are smaller, and different stars are different brightnesses. Take a pretty familiar constellation, Orion.
Here you see the constellation as it's seen from Earth. But remember, space is three-dimensional. The star on the left of Orion's belt is about 800 light years away. The star in the middle of the belt is about 1,300 light years away. And the star at the right side of the belt is about 900 light years away. Yet from Earth, they all appear to have the same brightness.
Some of the stars in the universe are amazingly large as well. The biggest star in the universe that we know of is 1,700 times larger than the radius of the Sun. 5 billion of our suns could fit inside it. We're going to need a bigger bowl, bigger fish bowl.
We've given you a way to compare the sizes of the planets.
And we've given you a way to create a scale model of the distance between the planets.
What if we took those two and combined them into one scale model?
Remember, we use scale models to help us understand really large numbers, and the sizes and the distances are so massive that it's pretty hard to put them together.
But fret not. There are scale models of the solar system all around the country.
There are plenty of creative scale models to be found across the United States and around the world. Doing a simple online search can point you in the right direction.
Want to tour the solar system in a day? Silas Education is building a scale model of the solar system in Washington State. It starts with the solar arches, a 40-foot sculpture of the sun designed to cast shadows which tell the story of the predictable path of the sun over the course of a year, and will have markers for each of the planets.
If you're looking for some unusual models, there's the flag solar system, where each flag represents a planet at Green Bank Observatory in West Virginia. There's the distance to scale model made of fiberglass planets on light poles in Traverse City, Michigan. There are plenty of walkable models. In St. Louis, there's the Del Mar Loop Planet Walk. You can find the sun station right outside the Moonrise Hotel. Check off each planet signpost until you find Neptune, located about a half a mile from the sun.
There are several Voyage solar systems. These walkable models feature scaled mock-ups of the sun and planets. and are about 1 to 10 billionth scale. They can be found in Kansas City, Missouri, Space Center, Houston, and Corpus Christi, Texas, and will be returning to the National Mall in Washington, D.C.
But if you don't have the time or energy to walk, there's the Solar System Lawn Model at the Griffith Observatory in Los Angeles, California. In this model, the planet's orbits are properly scaled around the sun. Each foot in this model is roughly equal to 20 million miles in our solar system. Do a search. Can you find a model in your hometown? We've looked at scale models. We've looked at the size of our planet, the distance between the Earth and the Moon, the size of the planets in our solar system, and the distance between them.
We've also looked at sizes outside our solar system. Where can you find or make your own scale models?
Map your neighborhood. Walk around your neighborhood and make a map. Think about what scale you'll use.
Build a scale model. You can make one yourself, or you can buy one. Notice the scale.
Think about how scale models are used in real life. The Navy uses a scale model to move planes around on an aircraft carrier called a Ouija board.
A lot of museums use scale models called dioramas, which allow them to represent scenes with three-dimensional figures. The Smithsonian's National Museum of Natural History did some with dinosaurs.
And there is an entire museum in Gettysburg of dioramas of famous Civil War battles. The interesting thing about this museum is that all the soldiers are cats.
The cats are not to scale, but boy are they cute. Do you have a scale model at your house or in your classroom? Have you found one at a museum? We'd love to know about it down in the comments section.
And if you like this episode of STEM in 30, be sure to follow us on Facebook and Twitter and subscribe to the National Air and Space Museum's YouTube channel.
And teachers, be sure to check out the Teacher Tips document with resources on how to use this episode in your classroom.
Thanks for watching. Scale is the ratio between the size of a given original object and a new object, which is a representation, but of a different size. But what if you wanted to calculate?
I didn't like mine anyway.
Okay. Would you stop it? Leave them alone. Stop.
Kiss fingers?
Yes.
It's 8 o'clock and Beth has crossed over the bridge to...
Stop touching things. Just stop it. Keep your hands to yourself. Now I can't remember what I'm supposed to say.
Size of the Earth.
To show how big the Earth is in comparison to the sun.
Why do you get to touch them?
Because someone is more responsible than how. No, we can just use this. If I spread my arms out like this is the size of the sun, which means the size of the Earth would be about...
One more time! One more time!
Ow!
I'm built different. And our solar system. Just go. Get on out. Leave. Please.
Back to